and it's going to shrink everything. So I got to zoom it back in. There we go. You learn to anticipate these things. Okay. Now, what we have is the theta versus t for the rotating beam. And our initial analysis told us that pretty plausible that the angular velocity is fairly linear. Okay, so looks pretty linear, but we're not absolutely sure because we did this with a hand sketch graph and data. It wasn't totally accurate, but actually our data is pretty good. Okay, so if so, then your angular acceleration is constant. And of course, we defined all these as the rate of change of your angle with respect to time. The angular acceleration, and we call that angular velocity. And angular acceleration alpha is a derivative of omega with respect to time, and that should be locked in. I think it probably is. Okay. It turns out that alpha depends on the frictional forces. Okay. And frictional torques, and we'll develop the idea of force and torque and how they work. We'll develop some of that today. So alpha results in frictional forces actually torques. And one thing we kind of know is that this is spinning real fast. It's churning up a lot of air, and that's taking energy, and that slows it down faster than when it's moving slow. Or at least there's more force on it. Faster you go. More torque, more rotational force, if you want. That's kind of what torque is, okay? To slow it down. And we know then that alpha really shouldn't be constant. Okay? So if alpha is linear, then alpha equals, I don't want to use A, B, and C, the parameters. So I'm just going to say all the letters have connotations. I'm not going to worry about that. Okay, let's just use U and T for the slope and intercept of the straight line alpha graph, right? And of course that relates to V here and slope. Okay, now this isn't this because this is alpha versus T. Okay, or maybe versus increasing. Okay, now we actually think it's decreasing. Think of air resistance. That's probably going to be a big part of it. So we kind of expect it's decreasing, but we don't know until we measure. And we don't know how good our measurements are until we test them. So we're going to test them today. Set up the same system, take your functions, and test each one. Okay. Now, another thing we're going to do is we're going to go ahead and use a clock instead of a pendulum, because you can start the thing moving and then come back and measure a minute. You know, it takes measurements a minute later. Okay. 15-second count or something like that, or count how long it takes to go through 3 revolutions. Now we add more accurate things. We could use stopwatches, but we're not going to do that today. We're just going to get a plausibility measurement. One thing is we have these interfaces, and some of you probably brought your computers, laptops. Some might not have. But we're not going to actually use these today, although I might set it up on my laptop and let you set it up on yours if you have it. Okay. And in the future, we'll want to bring the laptop because we can plug that thing into this little thing, download a simple program from Vernier, and take really accurate data. Okay. And we can set it up to measure the angular position of this thing 100 times a second if we want to. It probably is overkill. 10 times a second is probably sufficient, but this will handle 100 times a second. Your laptop doesn't mind doing 30,000 data points. Okay. So we can really test your models. Okay. Now, if alpha is linear, then if alpha is ut plus v, what's omega? Now, this is alpha of t, this is omega of t, right? So when I say what's omega, I mean what's the function? Now you took the derivatives of the quadratic, cubic, and quartic models on your data. So you know what those functions are for your data, provided the quadratic or cubic or quartic model is accurate to the extent that that model is accurate. So how are omega and alpha related? Discuss this for. Well, as I said, I thought somebody would immediately say, because you already found alpha from omega. Okay. But as I said, we're just in the early stages of learning that calculus is actually useful. Okay. That it actually has meaning in connecting things you learned in calculus with the real world. Okay. You did examples. But usually in a calculus course, you do examples. You see a key word and you say, okay, that word means I better do this, rather than understanding why the situation leads to this. I mean, it's natural. It's a stage in learning. And in calculus, you often just don't get past that stage. And again, I've said you lose track of the derivative being the rate of change. Okay. Okay, so anyhow, how are alpha and omega related? Well, emphasize the t dependence of these things and the fact that you're taking the derivative with respect to t. I'll write it out completely. And we can write it shorter. We just say alpha equals omega prime. Okay. Or even alpha equals omega dot. It's another standard notation for the derivative. You seen it? Yeah, you probably haven't used it a lot. You probably use this and this. That's common also, especially in upper level physics. And most of you won't get to upper level physics. Certainly, a physician's assistant doesn't need upper level physics, even though it's good for your soul. You probably have other things to learn. I'm going to digress on another thing. No, I don't remember exactly what the connection is. I'm thinking about this. It's just HDL versus LDL. Okay. I can never surely remember. I don't know what the connection is. I can't certainly remember which one's good and which one's bad. And it's important, because I got a tendency toward cardiovascular issues. Seem to be well under control. But the older you get, the more likely they'll get old. I think I'm already there. Okay, so it's kind of relevant, but the reason I never remember it is because I don't have a deep explanation of it. I don't know what's going on at the molecular level. Okay, so what I kind of think is that HDL is a good one, LDL is a bad one because LDL is lower density and it's more likely to smear over your arteries. That's not a deep explanation. That's an intuitive explanation. Okay. So, yeah, I don't actually think about why HDL is probably the better one, but what it is I had to look it up. I'm unsatisfied with partial explanations. I don't have time to get into the molecular biology because I'm really stupid with biology. Not stupid, I haven't studied it in depth. Okay. So I kind of remember that I looked it up. Okay, HDL picks up the LDL and helps get rid of it. Little fingers. It binds with it somehow, carries it off, and your liver gets rid of it. And that part is easy. Your liver's looking through the stuff in your blood. I know that much. Your liver's in your right shoulder, right? Anybody? Oh, okay. Well, you make a good physician's assistant because yeah. In your right thigh. No, this is right. Okay. Yeah. Okay. It's on this side about here. Okay. If I'd ever had a problem with my liver, I'd know darn well. So far, I've looked out on that. Okay, so at the end of digression, I'm just kind of meandering a little bit, but there's an idea of deep understanding, and that's the point I'm trying to make. Okay, I don't have a deep understanding of everything, but a fairly deep understanding of the mathematics of physics and stuff. And I want to give you a deep understanding because you have a deep understanding. Just like I said, what's the derivative of the arc secant? have a deep enough understanding that I know if you take the derivative of the arcsecant with its inverse function, you're going to get 1. Because the inverse function applied to itself gives you x. And the derivative of that is 1. And once you do that and know how to draw a little picture of a triangle, all that stuff comes right out. Then chain rule with the exponential function. So that's a little deeper understanding. And if you have that deeper understanding, then you have really useful tools. And that can be useful to an engineer. Kind of necessary for mathematician. Yeah, most of you want to be engineers. And you're going to be good engineers. I know that already because I've had you in a course already. Okay, so trying to address that. Okay, so back to what we're talking about. We've established that alpha is a derivative of omega. So if you have alpha t, you can get the omega. Okay, so how do we find omega of t if we know alpha of t? Okay, I'm glad I got a quick answer in that the integrate. Okay, I'll say more specifically, we'll find the general antiderivative, which is the same as integrating, and then adjust it to the conditions. Okay, because you have an integration constant. You have to figure out what that integration constant is in order to have a function you can test. You remember all about testing these functions, okay? Okay, so it's the indefinite integral of alpha t, which is the indefinite integral of ut plus v with respect to t. And don't remember, yes, if you're rusty in your integration, it's just the function, the general function whose derivative is this. Now, what function has a derivative that's equal to t? T squared over 2. Okay, so you're going to get a u times t squared over 2, because now if we take the derivative of this, u is just a constant. So we're just going to have the u multiple of derivative of t squared over 2. Derivative of t squared is 2t divided by 2, you get t, so you can get ut. Shouldn't have used ut. Yeah. Abbreviation, 2 schools. Okay, one 100 miles down the road, northern Texas. Okay. And I get to Austin often because that's my focus. And okay, so anyhow. And VT, UT and VT are about equidistant from here. Okay. So I didn't choose UT and VT, so we talked about sports, so we won't. Okay. Make sense? Okay, so we have our omega function, except we don't know what C is. It's an arbitrary constant. And why is it arbitrary? Why do we even have it? Well, because derivative of a constant is 0, it doesn't change. So you can have a constant here. And if we're going to make this thing work, you'd better have the constant here. Okay. Okay, so if what's omega of 0, you can kind of make the shape with your hand, or if it's a number. So omega of 0. See? Okay. Yeah, obviously, if t is 0, omega of 0 means t is 0, we're going to get C. So we're going to express C as omega sub 0, omega naught. Right? Okay. So now I'm going to ask you, let's see if you can do this. I'm just going to give you a minute to at least write out how you're going to do it. What do we do now to find theta of t? As soon as I figure out where to press for each one. Ideally, you'll have those functions written out. You don't have to go look them up. You kind of keep a notebook for physics. Matter of fact, you probably ought to have a dedicated notebook. And the official type lab, I've got one here. You get really nice lab books like that. Books will last. Yeah. Something like this. Got a grid. Very handy. Making more accurate graphs than you can by hand. Now, sometimes back of envelope stuff, you just sketch a graph. You should have that skill. You shouldn't need a grid to, for example, plot 6 or 7 data points and see if they look like it's a plausible straight line. So then you can go to more accurate and careful graph. Should be able to do a quick graph. Okay, let's see.
So I took the data.
Yeah, look good. Looks good. Yeah.
That was
Hold
my
it there
colleague
for a second.
here.
I'm just looking at what you have. Okay, scroll down to this one.
That's mine.
I almost need to put the classes. Okay. And yeah, so how did you do the derivatives?
When I was doing the derivatives of these.
Yeah. That looks good. That looks good. I'm not saying they're correct. I'm not checking your steps, but I expect that you're being careful and doing it right. And that all looks like it should, except
So
I think you might be missing a term on this last one. Make sure you got it.
this one, oh, let's see, 4.2x probably, because I probably should have
Yeah, you should have a
a constant.
0.28 x on this.
Okay,
Oh, no, actually, you're doing a derivative of x cubed, which is 3x squared, right?
3x squared, so then that'd be
Okay, well,
14.
let me just check your derivatives. These look fine, because I just looked at what you have. That's good.
So I guess I'm missing my constant on this one, because that would be an x, and then that'd be plus.
Yeah, okay, on this one, that is right. Yeah, that's right. Okay,
Mhm.
and on this one, I think you got confused about your number. It's easy to do that. It's going to be 3x squared, which is 0.0021. Right?
From the 4.
Yeah, look at this term. You're doing the derivative of x cubed, which is 3x squared, right?
Oh, okay, yeah.
And you treated it like
Treated it
2x
two.
squared.
So
Now, that's not the worst mistake I've seen today. I won't mention who made the worst one.
So that should be, that should be 21.
Yeah. So,
Okay,
okay, so you're gonna have a 0.0021 x. It looks like you took another derivative here. Okay,
so I,
and you're only gonna take one derivative.
okay,
Uh,
well, wouldn't this be my W and then this would be my alpha
omega, I'm saying, you're
or?
getting in big trouble. Okay, you're getting in big trouble, because who said I'm the alpha and the omega? Don't want to make that guy mad. No,
Yeah.
okay, no,
Yeah.
I just use that as a kind of a joke, but it's omega. And often W is an important symbol, so you don't want to confuse omega with W, even though it's tempting because it looks like a W. It's rounded.
Are you talking about, oh, for work? The symbol
Yeah.
for work, okay.
And other things that work most often. That's good insight. Okay, so you only need. Oh, wait a minute. Okay, so you should be labeling what you did. So this is omega. And this is alpha.
Right.
So here's omega, here's alpha. Here's omega, and here's alpha. So that's where you're taking another derivative. Okay, so that's good.
And then I'll need to fix
Yeah.
that.
Well, but the derivative of x squared is 2x.
Oh, so I need
And you
to,
did that here and here. So, you just got to be careful to take your derivatives carefully, because it's, you're a little out of practice.
so multiply this and then I'll get,
Yeah, you're going to get 2 times this here. Okay.
okay,
And then down here, well, this is going to have an x on it. It's actually going to be 14, right? You're going to have an x on this, and you're going to have a constant about 0.5. Okay.
okay.
You write out the decimals. Okay, so now the question is, can you tell me for this model,
Mhm.
what's omega naught?
Omega naught would be the constant.
And right there it is. Okay, this is my, right?
Yeah.
And what's theta naught? Well, that looks like it's 0. Okay. Although I think that your quadratic model score. Huh. Didn't have a constant, okay. I mean, if it did have a constant, it would have been a small one. So that's fine. Okay. Yeah. Okay. So you really ought to have all your derivatives with that. So okay. So you identify your number. So what is omega? It's what you get. Yeah. You can say it. So omega naught equals this, theta naught equals that. Write it out. I mean, it's real easy to identify. We just have to know which one it is. Okay, that's important. So over here, right on the omega naught equals theta naught equals. You've identified it.
It's there. There it is.
Yeah, but this is not, this is because that was function. Alpha is a function here. So This isn't, okay. And, actually, this gives you alpha, but this isn't alpha. That takes some derivatives. Okay. So make sure we have all this.